Hello everybody, welcome to today's AFMS seminar. Thanks for coming along even with the changed time. So it's my pleasure to introduce our speaker for today, Dr. Johan Larsson, who is an associate professor at the University of Maryland. His research interests include multiple problems in the field of computational turbulence. A couple of examples are wall modeling for large eddy simulations, grid adaptation for turbulence resolving simulations, and high-speed turbulent flows. And he's going to be talking about some of this work, specifically modeling and prediction of high-speed turbulent boundary layers. He will be speaking about that today. So please take it away, Johan.
Well, thank you very much for having me. And thank you for being kind to move the seminar by 3 hours. So this is downright civilized. I'm going to talk about the work done over the last maybe 10 years or something. So it's been supported by NSF, the Air Force, NASA, and the Department of Energy. And so that's gratefully acknowledged. And the work has involved multiple people over the years. So it started with Andrew Trettel, who did his master's degree with me. And then a couple of years later, Pedro Volpiani, who was a postdoc with me. And now currently, Vedant Kumar is a PhD student. And for more than 10 years or so, I've really enjoyed discussing all things compressible turbulence with Sergio Pirozzoli from Rome. So he's a longstanding collaborator. So I'm going to kind of assume that people have some level of background in incompressible wall turbulence today, and then focus the talk on what happens when you add compressibility to it. So just to give a quick snapshot of the state of the art or the state of knowledge in incompressible wall turbulence, we have the law of the wall, or the log law. And if you think about it, it's really quite amazing that you take flows from different geometries at different Reynolds numbers, and the mean velocity all collapses more or less, right? And so the log law then is this straight line in the semi-log plot. And now I would argue that the current sort of debate in the field of incompressible turbulence concerns things like what is the exact slope of the log law and where exactly does it start, for instance. So, but that's sort of a quick snapshot. Over the past 20 years in incompressible turbulence or wall turbulence, probably more attention has been paid on exactly what happens to the Reynolds stresses. How does the peak magnitude change with Reynolds number? What happens to an outer peak, and so on. So now in Australia, you have some of the best researchers in this area. So and you know much more about it than I do. So the only reason why I put this up is to maybe take a snapshot that this is the kind of spread between different results that we see in incompressible turbulence. So if we go to supersonic flows, then we see a larger spread. And so if we start focusing on the left figure here, this is the mean velocity profile, just raw data, but scaled with the friction velocity u tau and the viscosity to get u plus and y plus. And I've just plotted the mean velocity profile for a Mach 2 boundary layer. One has an adiabatic wall and one has a cold wall. And so what we realize is that it no longer lands on the log law. And so there is a vertical shift in the log law intercept. If you look very closely, you realize that there's a slight shift in the slope of the mean velocity profile there. And so if we look at the right figure, the streamwise Reynolds stress, clearly there is no collapse in terms of the peak value of the Reynolds stress. But more importantly, if you look at the location of the peak in y plus units, you realize that it changes. And it changes both with the Mach number and with the wall temperature. So that's the sort of takeaway, that when you go to supersonic speeds, U plus and Y plus and Reynolds stress is scaled with U tau. None of them are universal anymore. And so the objective of all the work that has been done in this area is basically to come up with theory that accounts for these Mach number and wall temperature effects. And so I also need to now take a little bit of a step back. So what happens when you take an incompressible fluid and you turn it into a compressible fluid? Well, one thing that changes is that you can now support acoustic waves. And so there's an extreme example of this here, which is a turbulent boundary layer that is radiating a lot of acoustics. Now, that is believed to be a of minor importance in this particular area. And what's believed to be of greater importance is that at the supersonic flow condition, you have non-uniform density and viscosity throughout the boundary layer. So that's what basically everybody who works in this area assumes. So it's, in that sense, it's not really a compressibility effect we're studying, it's a variable fluid property effect. So let's do a little bit of background here. And here I'm hoping that the audience has some background with incompressible flows, because the way we study wall turbulence tends to be that we assume a parallel shear flow. And if we go very close to the wall, we can neglect convection and wall parallel diffusion and maybe even the pressure gradient. And if we do that, the X momentum equation boils down to this balance between the viscous diffusion and the turbulent transport. And so then, and in fact, the sum of the viscous stress and the turbulent stress has to equal the wall shear stress very close to the wall. Well, so why am I spending time on this then? Well, it turns out that if you do this for the compressible equations, then you end up with the equations on the screen, and they actually tell you something important, because the first thing they tell you is that the covariance of, or the variance of the velocity field, what we term the Reynolds stress, is if you divide that by friction velocity squared, as we do in compressible, that should not be a universal quantity in a compressible flow. And the reason is that the X momentum equation tells you that the universal form of the Reynolds stress is when you multiply it by local density and you divide it by tau wall. Okay, and so this was discovered by Markovin in 1962. And so if I plot the Reynolds stresses from the previous slide, and so what I've done now is that on the horizontal axis, it's still y plus. So you can see that there's a horizontal shift between these three cases. So clearly there's no universality in the wall distance. But if you instead just focus on the vertical scaling, it's not perfect, but the peak values of most of these stresses are kind of similar to each other. So the Markovin scaling is something that's widely accepted as the correct way of scaling these. If we continue along this line, if I now, instead of analyzing X momentum equation, if I do the same type of analysis to the internal energy equation, I assume I'm in a parallel shear flow very close to the wall. Convection effects are small, wall parallel diffusion is small. Then I end up with the equation in front of you. So to the right here, we still have heat conduction and turbulent transport. So those are the exact analogs of the viscous shear stress and the turbulent shear stress, of course. And then we have additional terms. The most important one is the one in green, the viscous heating term. So sigma here is the viscous stress tensor, and it's multiplying a velocity, a fluctuating velocity gradient. And so that is the rate of dissipation of turbulence kinetic energy. So you have this flow of energy where kinetic energy in the mean field through production turns into turbulence kinetic energy. And when the turbulence is dissipated, it's dissipated into heat. So that becomes a source in the internal energy equation. And the remaining terms are pressure gradients multiplying velocities. So the pressure gradient is a force per unit volume. So these are work terms, but they tend to be smaller. But by and large, if we combine all of these, we basically have a source of heat that is approximately equal to the viscous dissipation rate. And so you can use this equation to understand that in a high-speed boundary layer, there has to be a non-uniform temperature throughout it. And one way to sort of estimate how big that effect is to take, if we go above the viscous layer here, so I'm going to assume that the turbulent transport term and the turbulent and the viscous heating term, the dissipation rate, that they are similar in magnitude. And if I now, first of all, I assume that the production and dissipation rates of turbulence kinetic energy are similar. And then when I replace the right-hand side with turbulence production rate, I make an eddy diffusivity assumption for both the heat flux and the momentum flux. So I end up with this. And if I finally estimate these gradients by taking sort of wall quantity minus free stream quantity divided by delta, I end up with the following estimate. And if I now solve for this, I have that the wall temperature T sub W minus the edge temperature, so edge of the boundary layer or free stream, that the relative change in temperature across the boundary layer has to be proportional to the Mach number squared. So that's a fundamental result. And so this means that the typical temperature profiles in these types of boundary layers look like this. If I first consider the case of an adiabatic wall, then I have a spatially distributed viscous heating from the dissipation of turbulence kinetic energy into heat. And that happens throughout the boundary layer. The wall is adiabatic, so I can have no heat flux through there. And then it makes sense that the peak temperature occurs at the wall. And of course, the higher the Mach number, the more extreme this effect is, as we just derived. It has to go as Mach number squared. The wall temperature at these conditions is important, and it has a specific name, so that's called the recovery temperature, or the adiabatic wall temperature. And so it's closely related to the idea of a stagnation temperature, but it's a little less because you're losing heat to transport away from the wall. So the recovery temperature is a direct function of the Mach number in this case. So what happens then if I place the wall temperature at something other than the recovery temperature, meaning, so now if the wall is non-adiabatic, then if you, for instance, follow the red lines here, so the top red line is an adiabatic Mach 4 boundary layer, and the next red line is a Mach 4 boundary layer where the wall temperature is half of the recovery temperature. I don't know, can you see my cursor, by the way?
Yes, we can see the cursor.
Perfect. So when you do this, then you end up having a non-monotonic temperature profile because we have a spatially distributed source of heat, and now we're losing, or we're having energy transported towards the edge of the boundary layer and towards the wall. And in fact, if you put strong enough, make the wall cold enough, basically like the bottom blue line, then you can again have a monotonic temperature variation, but increasing rather than decreasing away from the wall. So this suggests that the proper way to, if you want the parameter that describes how strong the wall cooling effect is, the simplest measure of that is just the ratio of the actual wall temperature divided by the recovery temperature. So if that ratio is 1, it's an adiabatic wall. If it's less than 1, it's a cold wall. Another popular metric for this is, it's called B sub Q for some reason. I actually don't know why, but it's basically, the best way to think of it is that it's the temperature gradient at the wall in viscous units. And so I'm going to use this parameter a couple of times later. And so just to orient ourselves, when I say cold wall, it may actually be very hot in human terms. So if we talk about atmospheric flight at Mach 3, the recovery temperature is about 600 Kelvin. And at Mach 5, it's about 1200 Kelvin. So any wall that is less than those temperatures is, from my perspective, a cold wall, even though it may be 1000 Kelvin. Okay, so that concludes the sort of general background on compressible boundary layers. And so now I want to go into a little bit of a history of theories proposed to do this near wall scaling, or theories proposed to recover universality in the law of the wall. So the pioneering work here was done by Driest, and he did a lot of important work in this area. I find it amazing that if you look closely, he actually was not an academic. He worked for one of the aerospace companies, and he still did some really paradigm shifting work. So that's truly impressive. So the most important work was in 1951, where he said that if you go into the log layer, the velocity gradient in the log layer should scale not as u tau divided by wall distance, as we commonly do in incompressible flows, but instead the velocity scale is the square root of the wall shear stress divided by the local density. So it has to be the local density rather than the wall density. And so that was his main thing. We nowadays tend to think of the Driest transformation as an integral transformation. And to my understanding, Van Driest himself didn't introduce that one. So that was introduced by Damberg in a PhD thesis. And so the recognition here is essentially that if you realize that if you look at these velocity gradients, if you compare the actual velocity gradient in a compressible flow, which has a 1 over square root of density in it, so basically what it means is that if you multiply the actual velocity gradient by a correction factor, square root of the density divided by the wall value, then you have an artificial corrected velocity gradient that should behave as an incompressible one. And if you then integrate it, you have an actual velocity profile. And so we call that a Van Driest transformed velocity profile. And the idea is that it's not the actual one we observe, but it's transformed such that it should satisfy the incompressible log law. And so the question is, does it do that? And so here I have 3 different supersonic boundary layers over adiabatic walls. If you just plot the mean velocity profile, they do not agree with the log law, as we've seen before. But if you apply the Van Driest transformation, all 3 of them agree beautifully with the log law. And so that shows you the success of the Van Driest transformation. Well, the story doesn't quite end there, because it has been known for quite a long time that the Van Driest transformation works very well for adiabatic walls, but not if you have a non-adiabatic wall. And in practice, in aerospace applications, the wall is almost always cold. So T wall over T recovery less than 1. The figure here comes from a PhD thesis from ETH Zurich in 2000. And so what you see here is if you have an adiabatic wall and you Van Driest transform it, the mean velocity profile lands beautifully on the correct log law, which is the dotted one. If you have a strongly cold wall and Van Driest transform it, you get the other result. So the slope in the log layer is correct, but there is a vertical offset. And so in fact, there are 3 errors there. One is a vertical offset. So the log law intercept, which is basically a measure of the vertical shift, the log law intercept is too high. The viscous buffer layer is too high, and the slope there is too low. So to look a little bit more at this, so if I look at this log law intercept, which is just, if I continue the log law down to y plus of 1 and I read off the value, that's the log law intercept, usually B or C. Usually we call it B or C or whatever. I call it C here. Damberg, in his PhD thesis, he collected adiabatic flat plate experiments. He Van Driest transformed the mean velocity profile and plotted the log law intercept. And you can see that there is no real trend with Mach number. So that sort of speaks to the success of the Van Driest transformation. Andrew Trettel, my master student, he ran DNS, so simulations of compressible channel flows. Compressible channel flows are such, I'll talk about it a little bit later, but they are such that there is the higher the Mach number, the stronger the cooling at the wall necessarily. And so as he went to higher and higher Mach numbers, or more importantly, to colder and colder walls, you have this consistent shift in the log law intercept. So the velocity profile is shifting up, up, up. Well, I guess this way. So the question then is, this feels very academic. Is a shift in the log law intercept really that important? And the answer is that it is. So if you look at the definition of the friction coefficient, it is proportional to the velocity of the value of the inner scaled velocity at the edge of the boundary layer squared, or the inverse of that. And so this means that the relative error in friction coefficient is about 10% of the shift in the log law intercept for most boundary layers. So what this means is that in the channel data here of Andrew Trettel, the log law intercept goes from 5.5 up to about 8. So a shift in 2.5, that's basically a 25% change in friction coefficient. So it is important. And of course, that's why we have continued searching for the ultimate near wall scaling theory or transformation. Well, so let's take a little bit of break from theory and just look at some applications, just to orient ourselves to where we are. So if I just told you that the type of intercept errors that we look at scale roughly like the bottom right figure, in a typical scramjet, so the high shot 2 is another Australian thing, of course. If I just use enormous hand waving to estimate the temperatures of the recovery temperature and the wall temperatures, I get that a typical scramjet would have a wall to recovery temperature ratio of maybe 0.15 in a ground test, in a short duration ground test, in a shock tunnel or something, and maybe 0.5 in flight. And so depending on those two values, this is roughly where I land in terms of wall cooling parameter. And so I would argue that, so what this tells you is that the estimated friction, for instance, will actually be erroneous to different degrees between flight and ground test, for instance. If you look at the high pressure turbine blades in a jet engine, again, huge hand waving, maybe you're looking at 0.6 or 0.7 or something. Arguably, those errors are probably small in terms of friction prediction. So maybe it's not that important for that case. If you go to rocket combustion, I actually don't know what the value would be, but again, it would be in the more strongly cold walls and therefore more important, right? So I would argue that these things are important for many applications. So let's go back to our theory track. So Van Driest did his thing in 1951, and I would argue that it had been known for quite a while that it was not very accurate for non-adiabatic walls. So when Andrew Trettel came, we tried to come up with a theory that was more accurate for those conditions. And so let me walk through a ton of equations here and tell you our thinking. So we said that what if you have a wall-bounded flow with known mean profiles, and then consider a transformed version of the same flow, but now where you have uniform density and viscosity. And so I'm going to use capital letters for the capital or hat symbol letters for the transformed state, and lowercase letters for the actual compressible state. So far, so good. So here we say that now imagine that we can write the transformed mean velocity as an integral transform of the raw velocity. So that's the second equation of these. That's the same as what Damberg did to Van Driest. The real innovation here, in my opinion, is that we also said that let's assume that the wall coordinate also needs a transformation. And let's not assume what that transformation should be. So we just said, let's write it as an integral transform. So my unknowns now are the integration kernels, capital U prime and capital Y prime. And just to sort of tell you that this is not unreasonable. So if you pick these transformation kernels in certain ways, you can recover sort of Y plus or U plus, or you can recover the Van Driest transformation and so on. So anyway, but we didn't pick them like that. We said, are there any ways that we can decide what these transformation kernels should be? So criteria number one was that we said that Van Driest's reasoning for the velocity gradient in the log law seems flawless. And so let's assume that he was right about it. So we say that du dy with lowercase letters is the actual compressible state. That should go as Van Driest said it should. And of course, if you apply the same thinking to a constant property case, then it goes like this. And so now it's just manipulations here of getting at these transformation kernels. And if you do, you have an equation that says that the ratio of these two velocity to coordinate transformation kernels should behave like this. So we still need another equation to solve for this. So our second equation was that we said that let's assume that Markovin was right and that the Reynolds shear stress has to be universal. And so what this means is the X momentum conservation for this idealized near wall flow says that the sum of viscous stress and Reynolds stress has to equal the wall shear stress. And so if I write that at the first line here is for the actual compressible flow, and the second one is for the imagined constant property flow. And so here comes the sort of the real reasoning. if we are saying that the mean velocity profile must be universal, then since there's such a strong relationship between the mean velocity and the Reynolds stress, that must also mean that the Reynolds stress must be universal. And the momentum conservation equation says that if the Reynolds stress is universal, the viscous stress profile must also be universal. And that has to be true even in the log layer where the viscous stress is neglected. So that was the part that I was the most uncomfortable with, because the viscous stress really shouldn't matter there. But our reasoning here says that even if it doesn't matter, it still should behave in a universal way. And so the outcome of this is that we say that the viscous shear stress basically should be the same in this sense. And that, again, with some manipulation, gives us a second equation that relates these two transformation kernels. And now that we have two equations, we can solve for it directly. And so the final transformations are that our transformed wall coordinate looks like the first one, and the transformed velocity looks like the second one. So here is an interesting observation. The transformed wall coordinate that we derived, if you write it in plus units, it turns out to be what we in the field call semi-local scaling. So this is something that actually had been seen before. It was introduced in 1995 in Gary Coleman, Huang, and Bradshaw, and perhaps John Kim as well, I think. They did channel flow DNS cases, and they, as far as I can understand, they knew that in order to collapse these Reynolds stress profiles, they knew that Y plus did a very poor job of it. And they basically tried a couple of different versions here. And they said that this Y star, which is based on tau wall and local properties, is the best one. So it was inspired thinking and trial and error. And so what we did now is actually derive that this should be it. And so, okay, so does this work then? So here are Andrew Trettel's channel flow results. He ran the channel at, so if he runs it at 3 different Mach numbers at the same bulk Reynolds number, the 3 colored lines don't collapse on each other. It turns out that it's a Reynolds number effect, because if you believe in this transformation, then you should consider the friction Reynolds number in the transformed space, not in the raw space. And so in the transformed space, we call that RE tau star. So it turns out that these cases actually have different friction Reynolds number in the transformed state. And so if I compare with the correct, sort of the corresponding incompressible DNS, then the match is quite good. And in fact, if I do this a little further, so here we have each of the figures has 2 different Mach numbers, but where the transformed friction Reynolds number is the same between the cases, and then they collapse really well on each other. So based on this, we said that for these channel flows, the transformation really works beautifully. And to just hammer home this message even more, if I go back to this log law intercept that I argued was so important for friction predictions, so if I have the log law here up to the left, if we take the transformed mean velocity profile back out what the log law intercept C is, if we use the Driest transformation, you have a scatter of this intercept all over the place. But with the proposed transformation that we did, it collapses really well. So there is a Reynolds number effect on this log law intercept that incompressible cases also sees, but the Mach number effect seems to be handled quite well by the theory. So this was a huge success. So then when we wrote this paper, we did look a little bit at boundary layers. We didn't run anything ourselves. We just went to some data in the literature. And for the data that we tried, it worked reasonably well as well. So at this point, this was a huge success, right? So what happened then, maybe 2 years later, was that Peter Volpiani came along, the postdoc, and he started running cases at higher Mach numbers and with closer to adiabatic walls. And when we then assessed the theory for this, we realized that there was a systematic shift away from the log law as you go to higher and higher Mach number, especially if you keep the wall close to adiabatic. So the orange and blue lines here are Mach 5 instead of Mach 2. And this was really puzzling to me. And the reason is that I have always assumed that there should be a universality between channels and boundary layers, that the inner layer near the wall should be the same. And clearly that is not the case here, because this transformation works in channels, but not boundary layers. And so what is the difference between channels and boundary layers? Well, so a channel flow is driven by a body force, which then necessarily performs work on the fluid. So that's an energy source. And the only way the energy can be lost is through the wall heat flux. And so this means that a channel necessarily has a temperature peak at the center line. And it also means that the wall cooling ratio is uniquely determined by the Mach numbers. It's not an independent parameter. And therefore, the nature of the temperature profile is quite different in a boundary layer compared to a channel. And in fact, if we plot the error in the log law intercept after applying the transformation, so the way to look at this is that the dark blue symbols means that the transformation works perfectly, and the yellow means that there's a quite large error in the log law intercept. So if we do this in a sort of Mach number wall temperature parametric space, it turns out, so channel flows have to lie on this dotted line. And so those are all the channel cases. So it seems like if you're on that line, the theory works, but almost all boundary layers are above that line. And then there is this systematic error. So I still don't know why that is the case, but we at least know when it happens. Okay, so let's fast forward a little bit then. So Pedro Volpiani, he was tasked to do shock boundary layer interaction studies, but he found this sufficiently interesting that he invented his own transformation theory. The way he did it was he again said that both wall coordinate and mean velocity are integral transforms. He followed the second criterion of the Andrew Trettel paper, and that gives him one relationship between the two transformation kernels. And then he wanted to use basically a data-driven approach. So he said, assume a general power law form of the wall coordinate kernel, and then let's just use data to fit these two coefficients. And so if you run a case and you try to find, for these two parameters A and B, where do I have minimum error? It turns out that there's a whole line through that parametric space that gives you equally low error. And so then the question was, how do we decide what exact values of these are the right one? Well, it turned out that the solution is you have to consider fluids that are not realistic. So air typically has a viscosity that goes as temperature to some power, maybe 0.7-ish. So we had to consider gases that had viscosity temperature relationships that were quite different. So I actually don't know what these other gases, if they even exist in nature, but that's what we considered. And if we did that, it allowed us to sort of nail down what is the right value of these parameters A and B. So that defines his transformation. So it's half data driven. Another part of the story here, this is work that was not done in my group at all. Chang et al., they proposed 10 years ago, they had an argument about production over dissipation and how that should be universal. And long story short, they ended up with an integral transform for velocity alone. More recently, last summer, a group with Griffin and Fu and I can't remember, Parviz Moin, I think, they sort of took that idea, they combined it with the insight that Y star is the correct wall coordinate, and then used the Chang idea. And so then they derived their own version of this, where they also have a transformation or an integral based transformation. So let's look at results here. So all these results are from this final, the last paper I mentioned by the Griffin group. And so the way to look at this is that the black curves are the incompressible results, incompressible DNS or log law or whatever you want to, something like that. And the colored curves are all from compressible cases that have been transformed. So we're looking for collapse to the incompressible value. And so what you see is that by and large, you see that, well, you've seen it before. For channels and pipes, Van Driest has systematic errors. The TL transformation works well for channels and pipes, but has systematic upwards shifts for boundary layers. The two most recent transformations, by and large, work better than the two older ones. So the Griffin group, they have a newer paper that's on archive right now, where they said, let's do the same comparison, but now let's go to more complex fluids. So high enthalpy boundary layers are warm enough that it's no longer a calorically perfect gas, for instance. And supercritical fluids are fluids near the thermodynamic critical point. And so if they do this, you get the slightly different story. The two oldest transformations here, Van Driest and TL, they still give reasonable results, not far from perfect, but reasonable. Whereas the more recent ones by Volpiani and Griffin now tend to be all over the place. And just to drive home this point even more, I think it's really useful to consider these unrealistic fluids. And the reason is that a theory like this should work not just for fluids that we see on Earth. They should be, the theory should be valid for all types of fluids. And so you can play with you can play games like this, where you say that the viscous length scale goes as viscosity times the square root of temperature. So you can design fluids to make the viscous length scale constant throughout the domain, or vary like it should in air, or the opposite of air. And so the group of René Pechnik at Delft, they've been using this trick for a while, and we have in my group as well. And so if you do this again, then you see this, that the two oldest versions here of theories work better than the newer ones. Okay, so how am I doing? 35 minutes. I have maybe 10 more minutes. So I've given you a sort of a little bit of the history of the theory development. And I've argued throughout that this is important for friction predictions. So let me tell you a more recent development about trying to use this theory for friction predictions. So this is all work done by my student Vedant Kumar. And so the idea then is, if you're in an incompressible flow, if you tell me the Reynolds number, I can go and use any type of power law to estimate what the skin friction coefficient is going to be. And so that's clearly extremely useful. And as you hopefully agree with by now, if you're in a compressible case, then it's not just the Reynolds number. You also need to tell me the Mach number, the wall temperature, and some details about the type of fluid. And so just again, to drive home the point that these effects are important, here I show you the estimated friction coefficients as a function of Reynolds number for Mach 2 and Mach 5 with different wall temperatures. So this is not 5 or 10% here or there, right? This is important stuff. The main strategy of everybody who's worked in this area has always been, just like with the transformations, the idea is to relate the compressible state to an equivalent incompressible one, and then use the log law. So the same is true here, that we want to transform a compressible boundary layer parameter to an incompressible one, and then use an existing power law, basically. And so the objective here of Vedant was to develop a slightly more general approach. So the state of the art is really Van Driest 2. So again, Van Driest, he did this in 1956. He used his new transformation to come up with an empirical friction formula. And so it very much is based on these things, where he translates the actual Reynolds number to an equivalent incompressible Reynolds number, finds the friction coefficient of the using an incompressible power law, and then transforms that one, right? Huang et al., they in 1993 developed a slightly different approach, where they assume an incompressible velocity profile shape, and then they use a transformation. They use the analytical Van Driest transformation inverse to actually get what would the compressible velocity and temperature profiles be. So in that sense, they provide not just the friction coefficient, but also the full velocity profile. So Vedant based his method entirely on this Huang method, and he just made it slightly more general. So the universal incompressible profile is based on a Prandtl eddy viscosity with the coal wake function, sorry. And So that's nothing special. At the moment, we have been using the Volpiani, not transformation, but inverse transformation. And then we need additional relationships. We need a density temperature relationship from an equation of state. We need a viscosity temperature relationship, and we need a temperature velocity relationship. So we take the most accurate versions we can find. And all of this becomes we have to do a numerical, we have to compute the inverse transformation numerically. So all of this is numerically done, and it requires some root finding and so on, but it's not a big deal. And we have a Python code. If you're interested, we can share it with you. So for validation, Vedant found several data sets that span Mach numbers up to 14, that span almost a decade of Reynolds number, and that span from quite cold walls, the blue symbols, to adiabatic in the red. And so here's the validation results. So what we're plotting here is, first, I'm looking at the friction coefficient. So these are all DNS data sets. So we know the truth. So we compute the CF from these different methods, and we look at the relative error compared to the truth. And the solid black line is 0% error, so perfect prediction. So what you see is the Van Driest 2 method and the Huang methods, they give very similar results because they're at the heart of it, both based on the Van Driest transformation. And so here you have these, as soon as you have the cold walls, the blue symbols, then you tend to have a systematic overprediction of the friction coefficient. And so with the proposed method, we get, there's less systematic error, and the peak error goes down. If we look at heat transfer coefficient, so the Stanton number, there is a slight improvement, but it's less pronounced. But by and large, we're going for maybe cut the error in half for the friction and just by a little bit for heat transfer. The method, of course, just doesn't just predict the friction coefficient and so on. It predicts the full velocity and temperature profiles. So if we compare these here the profiles are raw compressible states, so not transformed or anything. They tend to agree quite well. So this can be really useful. For instance, if you use simulations, if you do simulations, you want to do an inflow profile or something, you can use this. And how am I doing? Okay, I have a little bit more time. I do have a long-standing interest in wall modeling for LES. So just in one slide, super quickly, why is this type of work important for wall modeling? It comes down to, if you have a wall stress model, you tend to have an eddy viscosity of this type. And so this is a Johnson-King model with a Van Driest damping function. If you want to run this in a compressible case, you need to say, what is the equivalent compressible version of this? And it turns out that if you pick a transformation or a near wall scaling theory, you can then say which eddy viscosity is consistent with that theory. And so if you do the Van Driest transformation, this is the form of the eddy viscosity. And if you instead believe the TL transformation, it's very, very similar. The only difference is that you have to then replace the Y plus with a Y star in the viscous damping function. Is that important? So here are wall modeled LES of a Mach 3 channel. And so the point is that, yes, you see huge errors if you use the wrong eddy viscosity in the wall stress model. And the eddy viscosity, since it comes directly from the transformation, all of this near wall scaling theory work directly informs these things. So that's why it's important. And I should say that I did this maybe 5-6 years ago, but there have been more recent work, for instance, by Chang Yang at Penn State and Prahlad Iyer at NASA Langley, that I've looked into these things a little bit more. Okay, so I'm ready to summarize. So I find this general area really fascinating. I find the fact that we can have a problem where you can work in a very fundamental theory setting, and you can look for errors that are 10% rather than 1%. And even though it's this fundamental, it has a direct engineering application. I find that really great. And the other thing is, as I kind of alluded to at some point, having been thinking about the variable property wall turbulence case has actually changed my thinking on the incompressible case, because it has basically forced me to question every assumption that I've ever made about it. I hope you agree that there has been some clear advances over the last decade or so. Clearly, there's been an accelerating interest in this from multiple research groups. I think the minor advance has been that, like I said, we can reduce the errors in the predicted friction and heat transfer. From an application point of view, fine, that's maybe important. But I think intellectually, the much bigger advance that we've done in the last decade is that we have much more coherence in our thinking now. 20 years ago, it was not uncommon to find a DNS paper on this, where they would plot the mean velocity versus y plus and the Reynolds stresses versus y star. Which, if you think about it, makes no sense, because both mean velocity, I mean, the mean of a quantity and the variance of a quantity, they're just different ways of looking at the same underlying process. And the same underlying process should have a single wall distance scaling and not different ones. So I think we have made improvements in this area. And so what remains to be done? Well, we clearly still have not found the ultimate theory, because none of these are really perfect. I do believe that we can reduce the errors maybe by another factor of 2 or something. I think we have figured out how to use this to improve wall models. I'm not sure that we have figured out how to use it to improve RANS models yet. They are more complicated. So I think there's room for a lot more work to do. So thank you very much.
Great. Thank you so much for your talk. That was fantastic. I have some applause coming from the audience. So we do have some time for questions. So if you're in the audience and you have a question, feel free to just unmute your mic and ask away, or you can put your hand up in the participants list, or even just write it in the chat, and I'll try and keep an eye on the chat. But while people are kind of gathering their thoughts a little bit, so I guess this is quite a question. It's not a well thought out question, but I found your statement, I think it was on slide 15, where you mentioned that one of the results from the derivation was that the viscous stress appeared to be universal, even in the boundary, even in the inner boundary layer. That was, could you touch on that anymore? Because I found that very interesting. But
well, I can tell you that, well, I can show you the slide. I can tell you that when Andrew Trettel and I were fiddling with these equations, the second we came down to this final equation that said that the viscous stress should be universal in the log layer, I mean, my immediate reaction was, stop, we have done something wrong, because this is ridiculous. And I still, to some degree, feel that it can't be right. So, I mean, the argument I have, the only argument I have for, which I only half believe, is that momentum conservation says that viscous stress plus Reynolds stress has to be equal to a constant. And so I do believe that the Reynolds stress needs to be universal if the mean velocity is universal. So I easily buy that the Reynolds stress needs to be universal. And I guess if they both add up to the same thing, I can maybe convince myself that there needs to be some universality on the viscous stress. But the fact that it should be negligible means, I mean, there's something wrong there. So the answer is, I don't know. I do know that the final scaling theory is not perfect. And I suspect that that's one of my top candidates for what's not right there. But yeah, I agree with you. It feels wrong.
No, thanks for answering my question, my half thought out question. Anyone from the audience have a question they would like answered? Oh, everyone's probably, oh, we've got Ivan. Oh, you're on mute, Ivan.
Sorry about that. Hi, Johan. Thanks for a really nice talk. Yeah, very nice work. I'm just wondering, going towards RANS modeling. So then, you have to bring in other components of the Reynolds stress. I'm just wondering what your thoughts are about there, and whether you think the same approach can have inroads there.
To be honest, I haven't really thought it through. For the zero equation models that we use in wall models, then it's quite easy to sort of do the math and figure out how the transformation informs the eddy viscosity. But if we now do it for a K epsilon model or something, I honestly haven't. I don't really know. So René Pechnik at TU Delft, he has done much more work in this area. So he tried to apply semi-local scaling to the actual governing equations rather than just individual quantities. And they did derive some interesting things there. So he claims to be able to have a RANS model that is sort of has the correct behavior in the limit of high Mach number and cold walls. So I should defer to him instead of me saying something dumb.
Thanks.
Cool. Thanks, Ivan. We have Richard has a question.
Yeah, thanks for your talk. I had a question about pressure gradients. So I think everything you've presented is zero pressure gradient. How do you think favorable or adverse pressure gradients are going to affect things in the compressible world?
Again, I don't know. I do know that in well, I mean, to avoid answering a question, I do know that cooling the wall makes the mean velocity profile more full, and so it tends to be much more robust. It resists flow separation, right? So in a shock boundary layer interaction, if you cool the wall, you get a much smaller separation bubble. But that doesn't answer your question, because it's actually the opposite of what you asked. So, I mean, I don't know.
Is there any plan to look into that?
Yeah, I would like to. I find, in general, this is now I'm gonna become philosophical. It's easy to do simulations, but the hard part is having good ideas on which to test, right? And so at the moment, the thin sector is my ideas. So I need new ideas before I embark on something. But yeah, we should do it. I agree. We should look at it.
Yeah, I mean, I was just inspired by your example of a high pressure turbine, right? That has a very strong curvature, obviously, and you've got very significant pressure gradients in that case. So I was just wondering how that would apply to that case.
Yeah. No, we tried in a different project that was more focused on wall modeling. We set up these boundary layers with an arbitrary adverse or favorable pressure gradient. And so I have started playing a little bit with that. I mean, specifically trying to keep the boundary layer attached while exposing it to an adverse pressure gradient. So I've started playing with it. So I mean, I could do it for a supersonic case with a cold wall or something. So I think it's a good idea, but I haven't done anything on it. There was some work out of a German group, a Stuttgart-based group, only recently, where they looked at the effect of pressure gradients on compressible boundary layers. So I don't know if that's relevant. Yeah.
Okay. Yeah. Thanks for that.
Sorry, this is now the second question in a row that I can't answer.
Just trying to give you a grilling. We know it's almost midnight where you are, so prime time for difficult questions.
That's okay.
Anyone else from the audience has a question? All right. Otherwise, I think we might thank our speaker once again and let you finish off your day, basically. So thank you so much for that excellent talk. I'm going to stop
Thank you very much
recording
for having me.